moving on.
Great. So hi, you guys. Welcome. How many of you guys here have actually done a fair amount of F#? How many of you guys have done any? Well, I see 3 people in the back there. I don't think I've done one. Some of the other speakers for F# tomorrow, so I'm making fun of them. Good. So, hi, I'm Rachel Reese. I have been speaking on F#, I guess, for about a year. I started doing some intro talks. I have this one on agents and a couple others, but this is the second time I've spoken down here. I run the Vermont Functional User Group, so it's a generically functional group, but I speak there on F# all the time. So I am one of the only people, possibly in the state of Vermont, who knows and is interested in F#. So I bug them quite a bit. I'm just quite happy to be down here with other people who actually think a whole room full of people. So hi. So I'm speaking on F# agents today. So what are F# agents? Well, it's F#'s implementation of Erlang style message passaging, which is available in some other languages. I wasn't sure that would actually mean anything to anyone. Has anyone here actually worked with Erlang? Excellent. Almost no one. So, what is Erlang style message passaging? Well, it's based on the actor model, which was devised by Carl Hewitt. And if you guys haven't seen Erlang the movie, it is amazing, and you guys all have to go to YouTube and watch Erlang the movie. It's based in like 1985, and it has Joe Armstrong and Mike and the third guy, and they just sit around and answer telephones and say, "Hello, Mike. Hello, Joe." And it's fabulous. So the screenshot. So, Erlang's message passaging is based on the actor model. Well, what's the actor model? The actor model is a model of concurrent computation using actors, which is characterized by dynamic creation of actors, inclusion of actor addresses and messages, interaction only through asynchronous message passaging, and message passing, and no restriction on message arrival order. And that is a very, that's from Wikipedia, there's a very general overview of what it is that might mean. But without really knowing what an actor is, that whole definition really doesn't make sense. It's very much defined in terms of actors. So, what's an actor? Well, everything's an actor in this model, which is also, I feel like I'm really defining things here for you guys. An actor is an independent computational entity which contains a queue and receives and processes messages. So it is extremely lightweight. It basically, you can, I will show you guys in my samples, you can spin up, a couple 100,000 of them on your machine. It contains a queue, and from within the queue, it processes the messages that the actors will send to each other. What can an actor do? Determine what to do with the next incoming message, and as part of that, create more actors or send messages to another actor. That's basically it. You can't, do anything that does not fall into one of those 3 guidelines. That is absolutely it. And most importantly, one actor is no actor. They come in systems. So if you have just one actor, then you basically have the message queue. And it's a really lightweight message queue, and you probably can't do all of the things that you would expect from much heavier message queues, but there's not really a whole lot of point in just having one little guy sitting there. It's okay, it's nice, but So what do systems of actors look like? And this lovely graphic is Tomas's back there. But if we look at sequential and parallel, you guys have probably seen architectures that look like that before. Agent-based is all over the place. You have a whole bunch of different actors and agents, and they basically can send to each other. They can go back and forth. They, this guy here can send over to this guy, can send to this guy, but also to this guy, and it's a little more chaotic. You have to really not have the screen move around. it doesn't flow. It's much more of a massive system. There's also something like this. If you get a whole bunch of them, imagine that each one of these little dots here is a single actor. And there's this one here in the middle that can talk to all of these and then send out to the others. And there's a path from say this one here, go down over here over to say one of these out here, but it involves talking to several different actors along the way. It can get extremely chaotic. I showed this slide to one of my friends who said, wow, I've seen Erlang installations that look like that. It does not have to. It does not have to be so crazy. One of my favorite examples is something like a subway map. Imagine each station is actually an actor. And each train as it comes along is a message that comes in. So a message comes in here, the people get off, the train itself is sort of processed. Some people might transfer, get sent to a different actor and end up at a station down here, and that train will be processed. But one of the things that you can really see with this is that these stations, these actors down here, do not need to know anything at all about these. It doesn't. All you need to know are the actors whose addresses that you have, the next place to go in the chain, or the next possible places. If there's one of these stations here that has several different options, where you can possibly go, I guess in or out, but you don't need to know about all the crazy stuff at the periphery. So if we come back to this slide, the concurrent computation, dynamic creation of actors. So if you need additional actors, say you're processing something that can come in varied chunk sizes, and you get a particularly large bit of information, you can spin up new actors to handle that bit of new information. The inclusion of actor addresses and messages, which is what I was just talking about in the last slide, you can know where you're sending the next bit of information. Interaction only through direct asynchronous message passing. Well, the messages, like in the last slide, would be the trains. That's the only interaction that the actors would have. And no restriction on message arrival order, because it is concurrent and asynchronous. The messages can arrive out of order. It's not necessarily all the same. And back up here. So F-sharp agents are F-sharp's implementation of the actor model that I just showed you guys, which is the Erlang style message passing. So actually this link that I have here, if you go to the Wikipedia page, they list something like 20 different languages that all have actor models within them, and it's most of them I'd never heard of. It was kind of interesting, so you guys should go check that out. So one more quick definition, because I used concurrent in the name of my talk, and I know I've had lots of people discuss this. I wanted to define first asynchronous, non-blocking, specifically in reference to I/O operations. Not necessarily parallel, they can be sequential. It just means that when two things are talking to each other, it's not blocking. You send off a message, you don't wait for it to come back, you continue on doing something else in the meantime. Parallel, multiple operations actually process simultaneously. You have two different threads, both of them actually working, two things going on actually at the same time. And concurrent, multiple operations happening at the same time, but not necessarily in parallel. So, maybe it's on the same thread, maybe the thread is doing a little bit of one thing, and then a little bit of the other thing, and then a little bit of the first thing again, so that it sort of appears like it's in parallel if you don't look too closely, but it actually isn't. So I know that has come up quickly. How are you guys with the actor model? Are we good? Do we have questions? I went a little bit past the roll, but yes?
What do you mean by at the same time, but not parallel?
Yeah, It's when they're being processed, the thread might not necessarily finish the entire processing of it. So it'll process a little bit and then process a little bit of something else and then process a little bit of the first thing again. So it is sort of ongoing processing. It's just not continuously ongoing, as in the case of parallel, when it's like, say on two different threads, you know, it's utilizing the entire bit of one thread, and the other operation, whatever it is utilizing the entire bit of the other one. Does that? If I saw a great. There's space over here. Yeah, there is. Okay. There was a great little thing on Stack Overflow that showed basically in parallel, you know, two things go like this and it's continuous, whereas with concurrent, it's more like this. So that, you know, while this one's processing, this thing is not. And while this thing is not processing, this one is. Does that help?
Sure.
All right. Yes.
So these are, it's kicking off threads within the same process?
No. They're all within the process. That is one of the slight issues with the F-sharp agents. There is a new library I'll talk about at the end that does handle some of that, the F-sharp actor. But the actual F-sharp libraries are all within the process. But you can, it's still a much more lightweight. You can still kick off 100,000 of them easily. Like on my Mac, easily. Not on Tomas's phone, easily. So, but yes.
They go on the thread pool.
They go in the
Thread pool.
thread pool, yes. All right, so demos now. And can you guys all see that at the back? Is this big enough? Excellent. All right, so for a tiny bit of further confusion, even though most people will refer to them as F-sharp agents, when you actually get to writing the code, they're technically mailbox processors. Almost 100% of the code that I've seen will first just alias them to agents and then continue to refer to them as agents throughout the rest of the code. But just so you guys know, if you go to use it and try to actually type an agent, it's not going to be there. So even though I just said we should never have one agent, to show you guys how to do this, let's have one agent. So we call agent.start. You can also call another thing. You can define a new agent and then start it separately. You don't have to start it immediately within what you're doing. But a new agent is defined with a function, which is async, which has a loop within it. You'll receive the messages, and then here you're going to process them in the most profound of ways. Basically, this agent takes in the string and prints got message string, whatever it is. It's it's pretty intense here. So if we define it, and then the way to actually post to the agent is to know the name of the agent, the address of it, and it's all .post. There's a couple other ways, which I'll show you. You can post and reply, post an async reply, a couple other ways of doing it. But the most basic is to just do a simple .post. So, and then I'll enter, it says got message, hi. So it took this hi, stuck it in the string, and printed that out for us. So that is how the way you would create just one agent. So 100,000 of them, like I promised you guys. for loop from, 0 to 100,000. It's basically the same thing, receive a message. If for every 10,000th one, then print something out, just so I'm not printing out 100,000 messages, which might make my computer actually cry. And so here we go. For agents in all of them, just post a ping, and every 10,000th one existed and was there and got it. So that was 100,000 agents spun up super quickly. You guys have questions? All right. A common way of error handling is to actually have two different agents. So you can have an error agent, which takes, an ID or something with a system exception that just, maybe prints out an error. And if we have another set of agents that every now and again, if the message actually contains agent 99, because it'll have an ID and an agent, then fail for no good reason other than it contains those terrible agent 99 words. How dare it? So here's an example where I don't actually start the agents until later. So I, create these. I have, if there's an error here, then in this case post, with an agent ID and the error, which will be fail in this case. And then I start the agent, and then I return the agent ID and the agent. So let's. And then here for, this agent ID and agent pair, post just message to agent with an agent ID, which is how some of them will end up with 99 together. So then, everything that starts back from agent 99 to agent 990, then these are all the ones that failed and posted up to the, erroring agent and handled that. Got it, you guys? Excellent. So that was the basic intro. I'm going to get a little more complicated. One of the other things we might want to frequently do is get replies back. From an agent. So if you post to an agent, you might want to say, hey, yes, things are cool, or here's a message back from the information that you gave me. So it can be a two-way street. In this case, as part of your message, you have to send an async reply channel, which contains a string or an int or whatever you would want that to return. And again, I'm aliasing agent to mailbox processor. So here I have declare the agent, start it right away. The message here that I'm receiving, so the inbox receive over here, contains both a message and a reply channel. And then I just call reply channel.reply and send back this string up there, the received message of the message that I received. So that knows, which agent sent the message, and then sends that, and it's a return, a way of handling the returns. So to send the messages here, I'm using a post and async reply. I can use post and reply, but that will block. So you guys know, includes the reply channel, sends in an input and the reply channel. In this case, I'll run this example in a second, but I'm going to type in some information. We'll do a console.read line. That'll be the input. The reply channel is sent The start with continuations when it comes back with the reply is how you handle receiving that reply. So, you know, if you want to continue, if the reply was validly received, then you handle that in the first one. These two here, I didn't actually fill in, but the second one is an exception. The final one is a cancellation. So it's you have all three different ways of doing this. The my console app is also pretty crazy here. I post a reply. It's the one method that I was just showing you guys in the other folder. So if we run that, wait. Here we go. So, reply received message, and I can. It's sending it back from reply received, and up here received message. Should probably clean that up so it doesn't show you both. But it's actually going through and formatting the string only in the reply channel, and then sending that back to the first one, where it includes the reply received only on the start of continuations. So you guys have actual real proof that it hit both bits of code. Makes sense. Excellent. So in addition to replies, we can also you can also scan an agent. If you, for example, you had a couple different agents, and you just posted to one, and you wanted to scan for very specific kinds of responses, then it will process it when it finds a it'll scan through the queue and return the first one that it finds that matches your criteria. So if you say I want all messages that contain this bit of information, go find those. It'll scan the queue until it finds one and return back the first one that it finds. It'll leave the rest of the messages there. It won't process them, but you can process those first. So in this case, and both the replies example and the scanning one are both extremely similar to ones I have or ones that are out on MSDN. So if you guys want to go look at those, and my code is all out on GitHub as well, but just so you guys know. So this one basically generates totally mock jobs. It generates a random number and posts. I think I generate 10 of them or 100 of them. I don't remember, and then it gives me the option to cancel some of them before they have actually run. And so, you type in the number and it'll say, okay, I'm canceling job number 4, and it will scan the original, or one of the agents and say, oh, I'm looking for job number 4, can you find job number 4? And it'll return back job number 4, at which point I will cancel it, using the post and async reply, with a cancel exception down here. So I'm going to run this one first before I walk you guys through the code. So here, I'll cancel job number 3 and 7, and sometimes it's weird because it's random numbers like divided by 1,000 to figure out how long it's going to take, but it'll come back in a second. But you can see it started all of these, and then has job number 4, canceled these 2, and finished. Looks like the rest of them, not quite. Oh no, it is. So the way this works then, to create the jobs, like I said, is random numbers. It does an async.sleep for a bit of the a random amount of time to see how long it's going to actually take. And that's just, totally hacky random amounts of job time. So if the jobs are actually complete, then it does, then this is the agent that runs. So it starts, it has a loop, it receives the inbox, it has an ID and a result. That just says the result of the job, like you guys saw. Job number 4 is whatever amount of time, the random number that came back. And then it continues to loop. The in progress one is posted to every single time a job is actually run. And this one purely queues them. It's not meant to do anything else but hold them, hold a list of the potential ones to cancel. And because of that, we don't have, there's no internal function that actually acts on the queue in any way, shape, or form. We just hold them. So when jobs are run, or when jobs are posted, we receive them, we start a job, then we post to the in progress queue, just first to make sure that the in progress queue knows that some of the jobs exist, and start them, and we do this start with continuations. When that comes back, either it completes, if it does have time to complete. If it doesn't, then it was sent to cancel, and it'll say that we canceled it. To be able to cancel the job is when we use the scanning. So there we go. We want to synchronously check and cancel the job in this case. We do an in-progress scan, so we scan that one queue that didn't have the internal function, the in-progress scan, and send back a cancel method, a cancel action. If we find the job the job ID that equals the cancel ID, then we send back an option with with this action in it. So we need to send back an action to take if we're using scan. Otherwise, we send back none. So while I was messing with this code, I actually I think I put something here to say, print, we couldn't cancel that job because these two didn't match. And it will actually scan the entire queue, so it was sending back like 15 negative responses for every single one that it was able to cancel, because obviously it scanned the entire queue. So this is just it. I mean, it'll scan the first thing in the queue, it'll check that and say, oh, that job ID doesn't equal that cancel ID, and return none for that one. Does that make sense to you guys? Excellent. So that's how we handle scanning. So these are some of the little building blocks of agents. And then, just to confuse you guys extra even more, I combined all of these things into just a short little program that I built, basically an emailer. Lots of enterprise companies, even smaller ones, websites have a million emails that they need to send out. There's the welcome email and the I forgot my password because I'm dumb email, and the I haven't logged into this site for a million years, so please help with the email. I actually work for a company that handles grocery setup and such, so it's we have shopping list emails and recipe emails and coupon emails and millions of different things. So I thought it would be fun to use agents to solve this problem basically. So I have, we started the types. Can you guys actually see it if I leave it this small, or can you not see in the back? Are we good? Okay, good. Okay, I'll still up it. Fine. So I basically I have 3 different email types. Maybe one is the recipes, one is the I forgot my password, whatever. They're 3 different email types, and a discriminated union that is the message type, which covers all 3. So not a whole lot of types happening. And then we have to template them. So I was very hacky, and I have my very awesome templates here, and I have a templating function for each one of them that basically takes this incredibly important string here and just does a string not replace. Obviously, if this were a real thing, you would do this better. But so then I have a slightly different template that calls on the slightly different information that each of the types required. And then I have my data, just, some of them are type 1, some are type 2, some are type 3. They, just one big long array. It's nothing special, it's just a get data. Hacky data is hacky. Because what? I mean, this is how enterprises work, right? So I have all of my agents declared here, and I'm going to start from the bottom because the flow makes a lot more sense if we start from the bottom. And the way I actually set it up to work is I take that one giant array of data, I send it to my filtering agent, which filters by email address or by email message type into 3 new agents. It partitions these out, sends to 3 new agents which will actually do the templating, and then from there the 3 templating agents send to a sending agent, which prints, oh yeah, I sent the email. It's but from each one of those or any one of those agents, you can also post to an erroring message, which might log or something much more important. In this case, prints a message. Actually, in this case, it scans for one important error message and leaves the other error messages alone. So the filtering agent, like you guys can see, I mean, this is the loop here. I receive a message and partition those into types 1, 2, and 3, and then post individually to the agents that will do the templating, which are email type 1, type 2, and type 3. And then those 3 agents are, I have a generic templating agent, which takes in the templating function that I showed you guys in the template file. Basically creates the emails from the messages, the bits of information I send in with the template function, and then posts here using sending agent.post to the agent that will actually do the sending. And then here I define each of the 3 agents with the specific templating type. So are we good on that part? Excellent. The sending agent, like I said, not too I have a could fail here, so just to test out and make sure that the error handling is actually working. So if this fails, then I post the error agent. Otherwise, message number whatever to somebody with send. Here, I define could fail, and that's all the way up at the top, by either containing an an or an en in the email address, just to have something very easy and simple to check for. Yeah, and I put in two different failure messages. So from the sending, I post to the error queue, which scans here instead of just receives. So it actually scans for down here. If message contains cannot send, then it retries, and it actually resends back down to the original filtering agent so that it can restart that process. And it replaces an with a so that it won't fail a second time. And the errors that have The email addresses with EN are just basically ignored. I guess not entirely ignored, but they're, what do I do? Oh, I just say message failed permanently. So I might log this as something that we don't care about, we need to work on later, but we know that this is an ongoing issue with the system and we'll handle it. Whereas these down here, we definitely want to retry, and we have a way to do that that will then repost back down to the filtering. Does that make sense to you guys? Excellent. And then, like I showed you, that's my super awesome could fail. And again, the actual, my main is pretty basic. I get the data and I post it to the original filter agent. But if we, yeah, cool. So if we run this one, and one of the really cool things that I didn't point out about the code is there we go. I had a lot of parallelization in this. I did a lot of like array.parallel.map to send the stuff all over the place. So obviously these show up all out of order. Some of them are sent, we say, here, message 7 failed permanently, but this one to Sandy here, whichever one that it was, is, we're retrying that. That must be 27 because then it's retemplated. And somewhere down at the very end, there it is. Message 27 to Sadie.test@test.org was resent. So one of the things that I guess got me interested in agents to begin with was, or one of the early things, was listening to Joe Armstrong's talk at Lambda Jam. And he talked on self-healing systems that scale. And this is one of those ways that you can, I guess you can do this in other ways, but being able to reroute that and resend and retry and fix what's going on seemed like an important part of the agent architecture, I guess. So does that example make sense to you guys? Pretty good. Excellent. So, back to slides. So what are some of the major differences then between F-sharp's agents and Erlang's message passing? They're all contained in process. They're not actually distributed. One of the things that was one of the hang-ups that the team had. Lack of support for supervisors. One of the other things Erlang can do is have a supervisor agent that can spin up new agents sort of as needed. My early example of if you get in a much larger chunk of data to be processed than you're used to, you can just spontaneously spin up 10 new agents. That's, I guess, most easily handled with supervisors. And F-sharp does have reply channels, and you can sort of make it work, but it doesn't flow quite as well as people who have worked with Erlang claim, because I haven't actually personally worked with Erlang, so I can't claim this. But so they tell me. And no built-in durable mailboxes. So from what I understand, if the agent crashes in the middle of it, your queue is actually lost. And obviously that's not 1,000,000% desired. It would be ideal if there were ways to fix that. So one of the libraries that currently seems to be doing that is this fsharp.actor framework, which I spent a little bit of time playing with the last couple days, and really seems to handle a whole lot of this. So the Colin Bull, who is writing a whole lot of this, I'm actually working with his master set, right, or a bit of code right now, and I know he's completely rewritten the demo version or whatever the one that he's actually working with. So it does work in a slightly different way than I will be showing you guys tonight, which is actually better, but it does still actually do all the things that he is intending to do, which is make them distributed and make supervisors really work. You're able to link a bunch of things. So if we run so actors look very similar to begin with. They inherit from an I actor, but it's still very similar. You do a receive here, and you act on them. This one is just there's an addition one down here that's pretty much the same thing, and a multiplication one. You post two numbers, and here the result is a times b that it returns. The addition one, obviously a plus b. If we define these, addition, and then we have a calculator that, in this case, spawns the two of them. So their address here is now calculator / addition and calculator / multiplication. And then we can post to them since we know their addresses. So anyone who knows the address of calculator / addition can just post to it like that, and we get down here 5 times 2 is 10 and 5 plus 2 is 7. If we change the code, if we know the actual the array that the calculator had, and we know which one it is, then we can post specifically to that one. Enter, so that that's addition 0, so it returns 5 plus 2 is 7. We can post to everything that's in calculator by using the star. So we can take 5 and 2, and if we had a division and a subtraction, we can post to all of those all at once. And that basically does exactly the same thing. We can post similarly to the entire system of factors. So if we have something that has, so again, calculator, it's the same thing. It'll post 5 and 2 to everything that is under under a calculator that is basically the same thing. If we try to post to something that doesn't exist, it'll result in an error. Or it's not found, it won't return anything. We can also kill actors, which is kind of fun because, that's what fun things, right? So it prints out the status, and this one is shut down, obviously because I want to. It seemed like a good idea at the time. And again, you can post to it using actually calculator.1 or calculator / addition. Either way, we'll actually post to the calculator itself, or to the addition one. This is fun. You can change. Excuse me. You can define a mutually recursive function here, and so the first time you post to this actor, it'll respond with ping. The second time, it'll respond with pong. And spawn it, and then just keep posting ping pong, ping pong, ping pong. It amused me earlier. You guys don't have to laugh. Yes.
What's the double bang operator doing there?
I'm actually not 100% sure. I am guessing that's a. I did not find out this file. That is. I'm not sure. I'll look it up afterwards. But yeah, what?
That means in the precise type signature will not.
Yeah, that's actually a good idea.
Oh yeah. I quit using FSI because it kept crashing. So I actually don't. Yeah.
So that would be the lookup of the named actor string. So
Oh. Thank you.
Because otherwise it'd have a question mark on the right-hand side.
Oh, okay. Okay, so that's the lookup of the named after the
That
county.
makes sense.
It's very similar to Erlang, so you know you can cut down on
All the one people who know Erlang here.
From what I've heard of Erlang, this seems very Erlang-esque.
you know, you push the senders with the arrow.
Okay,
So-
okay.
And the matching, the pattern matching, looks almost identical. So if you get this, you'll get Erlang
Sweet.
for free.
So learn this, gain your link for free. Awesome. You can link actors. So if you spawn up a whole bunch of children actors, you know, A child, %D, 0 through, I think it was 4, because I'm spinning up 5 of them. And then spawn up a parent and link those, then, you know, it's, you know, spins up a bunch of them, and then once you have them linked, you can forward messages or send messages to the parent that will forward to the children. So, you know, just send the one to the parent, and all the 5 children actually received it, which is pretty cool. You can unlink them, and then when you try to forward to the children again, it's just 1 to 4 because I unlinked the 0 and 1. So that seems like it would be super useful. The actual supervision, we have an error here. I guess an erroring supervisor. Yeah, so in this case, it's supervising all of these, and if one of them actually fails, it will restart just the one I think that errored, and not all of them, just sort of as needed, which is what I went through quite a lot of work to mimic with, you know, getting the information that I actually needed and then posting down to the filter agent at the end of my code. Really? And then here, yeah, restarting supervisor. So it will automatically restart that one because the supervisor knows it failed, which I know is a big Erlang thing to make it that easy
So,
to do this. Yes.
question, if that actor failed and then gets restarted, so messages in its queue are not lost?
I believe they're not. I checked out the code a little bit. I didn't play with it and verify, but it seems that they would, yes, they would stay there. And I know that's one of the things that he is interested in making sure happen.
So the queue stays alive as long as the parent process is alive?
Yeah, as I understand. I'm not, don't quote me on that. I'm not 100%, but that's what I understand to be the intent. Is that?
And what about spinning up other processes? Is that possible in this library yet?
Yes. Remoting is.
Or am I stealing your thunder? Is that coming up?
I'm glad I placed you in the audience to ask that very question, Jack. Am I done with this one? Oh, you can spawn all of them if one of them errors as well, but if we move on to remoting, then I don't know if you guys have used the Fracture library. I had not heard of it before this, but they use Fracture to basically be able to post to any address using that syntax. So it's can be properly distributed, yes.
And then the health of a queue that's going to that process is dependent on that process staying alive.
Yes. Actually run these. I don't know that I. So it was able to post to, yes, sir.
Doesn't it serializable to go?
There's some serializing. I don't really know how he does it because I haven't delved into the code too much. Phil had answers before. I'm sure he knows them now.
Rachel, just tagging on to Rick's question, is there any example currently that doesn't use primitives?
No.
So the
So-
answer is we don't know.
Yeah.
Okay, cool.
And that might be in the demoing library that he's currently creating,
Right,
but
but
yeah,
in the current samples, it's not. there.
exactly. Okay. And these, by the way, these are all actually call-in samples. These are not mine. When I grabbed all this code off GitHub, it came with beautiful, beautiful samples. So if you guys want to go download and play with this tonight, that's all there.
So the stuff that Colin and Simon have done is actually based on their work at E.ON, which is a very large power company in Europe. And so this has been used for this kind of code has been used for several years in high volume trading. So it's fairly
awesome.
well grounded. I just thought I'd add, it's not just some guys who've done it for fun. They kind of know what they're doing because they've done it professionally.
Nice. Okay. It does show. But, so that's actually basically all I had. I have one final slide that has 1 billion additional resources. And I will additionally plug Prog-F-Sharp, which starts tomorrow. And you guys should all be there.
Tickets are still available.
Yeah, stern, glary face. But if you guys have any other questions, let me know. Yeah.
So some of the power of Erlang is OTP, sort of like all the gen servers and some of the behavior infrastructure, some of the infrastructure they've written around that.
Okay.
And so I'm sort of curious if the F-sharp community has sort of looked at like sort of mimicking the OTP library because that's what gives you the supervisor tree and gives you the FSMs and like all of this.
Yeah, it's an interesting question. I think there's two ways to look at it. You can try and rebuild everything, and then you can also just use it. And Erlang can play quite nicely with F-sharp. So Daniel Moll has entry on his blog about how you can use OCP, the OCP libraries with F-sharp. So there's layers on that. And I would say the languages are quite close, so why not use both? It doesn't have to be pure F-sharp. So maybe you can orchestrate.
And just looking for professional environments, right? It's very unlikely that you're going to get the Erlang and the F-sharp guy sort of, full skill set. So some of the management.
I have just a quick plug. I did a talk with Jan Kui, who works in social gaming, to the Erlang community on the Mostly Erlang show, and we talk about how you can interact between F-sharp and Erlang in quite a lot of depth, probably more depth than we can do here, and that's online, Mostly Erlang.
Another question. So I remember with the F-sharp built-in stuff, there's a sort of channel model for getting data back, the channel handle kind of thing. I haven't used it in a long time. There's something like that would be, I mean, I've never used Erlang, but is there something like that in Erlang, or is it in this? You know what I'm talking about?
I don't actually know Erlang.
Which he's asking if there's an equivalent of an async channel.
That's what I was, yeah.
In F-sharp active.
Oh, an F-sharp actor. Not that I have come across. And I only know those 3 pages of samples really well. So I'm guessing not based on those. But that's not a tremendously useful
I'll
answer.
poke around.
Yeah.
I can't remember if it was Joe Armstrong, so I don't know Erlang either. So one of the things I took from, I don't remember if it's his talk or one of the peripheral discussions was that I guess Erlang depends on spinning up a lot of actors, essentially, to go down the pipeline to whatever work they're doing like this, but then the messages that get passed back up, it also then spins up more actors coming back up, and the reason for that, I guess, is to avoid overloading the same thread. So you can have bottlenecks on threads, apparently, and because it's concurrent processing, you know, if everything's going through a channel and then coming back, you essentially.
Channel is like a one-way thing. It's like, I think
Oh,
if you get
okay.
a sharp one, there's no real way to get a result out of an actor. It's like you can send it messages and then somehow you can send, you send it the channel and then it can reply to you over the channel.
Yeah.
Build
Yeah.
stuff.
Yeah.
And, but in this, it seems to be able to actually send stuff back. I get it. I'm really sure.
Yeah, I just got the impression that it's possible and, you know, the systems that they implement to overload the same thread, so you want to, which is why I was asking all the questions about, you know, the process, spinning up multiple processes.
Yes.
I guess, you know, what these, it seems similar to me, this whole agent thing too, just passing around events. I mean, you can define events, and that's like defining messages. And they've got all these great functions now to like filter the events you're subscribing to and call your function when that message is sent. So why would I use one versus another?
Alright, Bill, this one,
Yeah.
the principal difference is in the addressability. I mean, if you think about it, what you're doing with the actor model is you're saying, there's a thing at an address that I'm sending messages to. Whereas with an event, you've got the record of the data, the message in transit, but from a modeling standpoint, from a system standpoint, you don't necessarily have a concept of the thing generating the events being other than some opaque thing that events spew out. You don't have this concept of, I got a message from an agent, I'm going to then, you know, do something with that. It's partly a modeling thing, there's also partly some implications depending on how your event system works. Like if you're talking about eventing like as it's done in the CLR, that has very specific architectural constraints around things like performance and scale and whatnot. For example, events wouldn't leave a process because of the way they're implemented in the CLR. So.
Yeah, right. But if it's all in process, you know, how does one compare to the other as far as performance?
As far as performance,
Yeah.
I don't know that there's a tangible difference in terms of if you're like measuring clock time,
Yeah.
but there can be a huge difference in terms of conceptual model. There's also potentially state management to consider.
Yeah.
I mean, very often what people wind up doing with events is events represent very small, opaque bits of state. And your messages between agents typically do as well, except that the agent itself is keeping some state potentially, and that's sort of not a salient feature of eventing as a cognitive model.
No, you have the mutables and stuff.
Yeah, and it gets
Yeah.
kind of messy.
Yeah, you're right, it's a little cleaner, a little more specific.
But again, not for every problem, you know,
Yeah.
for some problems, events do make more sense, you know?
There is another feature, at least, like I'm not expert on this, at least the F-sharp, like mailbox model, is that you don't just get an event and it pushes behavior on you, like with a CLR event, you know, it makes you do something right now.
Right.
This is like a thing that you can look through, look at priority events.
Right.
Yeah.
Yeah, okay, that's good.
Can I just expand the question a little bit? What would be the difference between, say, using this particular approach and something like 0MQ?
Ooh, can I field this one too?
Yes.
I do a lot of work with 0MQ. I actually am the author of the F-sharp binding for 0MQ.
Okay.
So there's
I've used your binding.
excellent. You're like the one person on earth besides me who uses it. That's great. So cognitively, in terms of like the model of actors, 0MQ is implementing the same thing at a slightly different scale and with a slightly different focus. But in terms of this actor-based model of zero shared state message passing, and that's how you're going to do all your concurrency, all your distributed computing, it's the exact same model. The main difference when you look at something like 0MQ is they're setting the lowest common denominator to be the protocol rather than the language. So that's the major trade-off there. Is yes, there are ways to, for instance, interoperate Erlang and F#, let's say, but by and large, you tend to look at the agents in the system all being written in one language, whereas Zero and Q kind of looks at agents as being anything that understands this protocol and this message. But it's the same conceptual model. You've got queues, you've got things that don't share state, passing messages to one another, and really they all model their behavior in terms of, I got a message, I do something with it. Whether it's ignore it, log it, send it to another agent, take some other action. Same sort of idea. Shameless plug for Zero and Q, it also does implicitly do persisting messages, not only beyond you, subject to the integrity of your the equivalent of an agent, but beyond the actual process. So you get small scale reliability out of the box in that case, because they've taken a slightly different approach architecturally. But it's conceptually, it's the same model. It's actors, it's agents, it's message passing, it's zero shared state, and that lets you do concurrency, it lets you do parallelism, it lets you do asynchrony, it lets you do distribution, so on and so forth.
Did you ever get a chance to benchmark the two approaches? I achieved very good scalability in Zero.
Oh, truthfully, I tend to use, I haven't done a lot of work with Erlang. I've used Zero and Q for a certain set of problems, and I use F# agents for a different set of problems. So I haven't ever really benchmarked them against each other, because cognitively, I look at them as fitting in a slightly different space. But yeah, I've seen both of them scale to thousands and hundreds of thousands of nodes. So, of course, the other benefit to Zero and Q, because it's taking a protocol-centric approach, you have a built-in interop mechanism between the 40 or 45 languages that have bindings to it, or really anything that will understand your message format or the protocol. So.
Very nice. Excellent.
Awesome. Thanks for